Let me briefly introduce myself, reintroduce probably. So I am Mr. Jagat, and I am an artificial intelligence researcher, and also I head a data science team for SIXT Research and Development, and I am based out of India. So anyone, if you have any questions which you really couldn't ask during this presentation, can reach out to me on this email ID. I'll be glad to clarify any questions you have. So yeah, the topic which I'll be discussing is about diarization, speaker diarization systems. So so I'll be talking about what is speaker diarization and what are the existing techniques used, and what is something which I have proposed innovatively in my paper, which suits the problem which I try to solve for my company and for my research. Okay, so I hope everyone is able to see my screen. Yeah, so let's go ahead to the second screen. So yeah, let's talk about speaker diarization. So in an audio file of where multiple speakers are speaking, the problem is to identify which speaker spoke when, right? Say for example, in this picture, you can see there is a speaker one who has spoken in the start and probably in the middle somewhere. So can we automatically identify which speaker is speaking when? Okay. This process of identification is called diarization, and there are many useful applications for diarization, such as transcription services, like and meeting analysis in companies after having a group meeting, probably analyzing and sending minutes of meeting automatically and so on. And even in broadcast media, speaker diarization is very useful for captioning the speakers when creating the subtitles. Also in call center analytics, speaker diarization is very useful. Yeah, there are several other places where diarization is super useful, I would say. So my inspiration came from this forensic analysis. I was doing a project related to forensic analysis and trying to analyze some audio recordings for crime investigation, a large database. So that inspired me to look into this problem, basically. Yeah, cool. So yeah, let's review the existing methodology. So once we get an audio file, we segment them into very small temporal segments, I would say. Let's say if you have a 1 minute audio file, you will be dividing that into very small segments like 15 milliseconds or 20 milliseconds. And then we apply short-term Fourier transform, and also we denoise and normalize. Denoise as in there are some environmental noises in audios usually, so we try to denoise that using some filters. Yeah, and then we create something called X vector or I vector embedding. So it is very similar to uh, the text embedding which you are seeing for BERT and maybe even the chat GPT, right? So it is doing some sort of a embedding. Similarly, for audio, we do some embedding called X vector embedding or I vector embedding, and that is the feature, a feature space. Okay, and the way it is trained and inferred is either using some clustering techniques or using some supervised learning. Uh, Recent studies say that the probabilistic linear discriminant analysis is most effective when we are using supervised learning. But the issues with these current methodologies is the clustering is totally blind, and we just try to minimize some loss function something like BIC, Bayesian information criteria, or something similar. And to train a supervised method, it is very costly to label all the data. Like if we have thousands of audio recordings, labeling them is a very big challenge. So yeah, which was, so I would say that in the project which I have worked, they didn't really have that kind of budget. So I came up with a different approach, which didn't really require exhaustive labeling. I defined something called loosely labeled data. Loosely labeled data is given an audio file. If we just know how many speakers are speaking in that audio file, that is enough. That can be used as the target variable instead of uh, detailed annotation. Okay, so that is the definition of loosely labeled data. Yeah, now let's get into more details. Let's assume the data set is like AK and TK. AK is the audio file and TK is the number of speaker in the kth audio file. Yeah, so yeah. Overall, at a high level, the process of training and inference is depicted here. So we didn't really have a lot of data initially, so I researched some online resources of data, and I synthesized the data. Say, for example, from SLR, there is I mean, you can review my research paper and you'll find the links for these freely available audio data. So using these, I generated these are one speaker audio data, but I created multi-speaker audio data by using augmentation and other techniques. And finally, we had several English audios, Spanish audios, and Chinese audios, and you can see some summary about the data which we created. So more details. We do X vector extraction. Like I told, I'll be skipping the denoising and other very trivial parts. So we do X vector extraction from the audio files generated in the previous step. And there are actually standard libraries. There is something called Kaldi project. Also, you can look into Hugging Faces. That's a Python library which you can use to extract X vector embeddings for a given audio file. Okay, so this is the block diagram. Like xt represents the teeth frame, milliseconds, 15 milliseconds frame, and there are some convolution layers and then statistical pooling layer and so on. This is not something which I have invented, but this was pre-existing. Like I told, it's already implemented in this Kaldi project. So you can take your audio and train it and get the X vector embeddings from the existing standard libraries. And this is the high level architecture of the neural network which is used there. Okay, yeah, let's get into the details about how I formulated the problem. So as I told, AK represents the kth audio file, and the first step is to slice this audio file into temporal segments of 15 milliseconds each. And then we can take any abstract similarity metric like cosine similarity, L1, L2, or any similarity metric which satisfies all the rules of similarity, and create a similarity matrix for a given audio. Okay, and this is a step we do for all the audios from 1 to n. Okay, now let's define a function gp, which is which is a from similarity. From similarity set to it creates a adjacency matrix. Okay, I'll go through the details later in the later slide. But yeah, this is pretty much technical part. Okay, so let me tell you what is the objective by showing pictorially what we are trying to do. Okay, so let's assume that this is the matrix which with the similarity metric, and you can see the edge weights, right? These edge weights represent the similarity between the vertices, and the vertices are different timestamps audio frames for a given audio file. Okay, now let's assume that P is a similarity cutoff, P is equal to 0.2 is a similarity cutoff, which means that any edge below 2 can be removed, and above 2 we consider that they are similar, as in they are voices of the same speech, right? So that's something which we do. And yeah, with P is equal to 0.2, you can see that we this fully connected graph will become like you will have two connected components if you have P is equal to 0.2 as a threshold. Okay, so in my paper, I have formalized the approach to identify what is the best P for a given set of audio files to optimally identify, optimally train our diarization system, actually speaker diarization system. Okay. And yeah, let's go to more matrix illustration. Yeah, if this is too complex, probably you can go through my paper as well in few, after my presentation. But yeah, let me just illustrate what I really mean. Let's assume that A1 is an audio file 1, A2 audio file 2, and so on, and they have similarity matrix. Okay, so this can actually be represented in the matrix form, and in the matrix form, it is something like this. So each of the matrix is for a given audio file. Okay, now we evaluate P. We'll try to compute what are the connected components at P is equal to 0 0.9, 0 0.7, 0 0.3, etc. Okay, and you can see so here I have defined the loss function, which is Q, and we are seeing the loss function for different values of P. Okay, so yeah, we can see that loss is least at P is equal to 0 0.3. Okay, which means that it is able to identify how many speakers are there in each of the audio file the best. That is a common threshold which can be used across the files, and it's not very specific to one audio file. Okay, so that's what we are trying to search. And you can clearly see that this is not a continuous law, continuous and differentiable loss function. The way it is defined in the paper, it's not continuous and differentiable loss function. So we need, the gradient or subgradient methods really don't work in optimizing in this kind of a scenario. So what I have used in my paper is genetic algorithms. There are several other ways like bisection method and several other ways which can be used, but I have used genetic algorithms in my paper. And yeah, the speech diarization is evaluated using a metric called diarization error rate. Okay, and you can see what is the definition of diarization error rate from here. Okay, so how many times we are matching with the right speaker, how many times there is a mismatch, we are labeling the speaker differently, and how many times the silence is being categorized as a speaker, and how many times speaker is being categorized as silence, and so on. We use all these differences and we compute the diarization, average diarization error rate. Okay, so this is the evaluation metric which we use. to evaluate any diarization algorithm. Okay, and yeah, I have evaluated on several samples with, but here I'll be demonstrating only one of them. Like I used cosine similarity, L2, L1, and something called Kendall's tau. These are the different similarity metrics, and I used my approach of genetic algorithms and finding the similarity threshold. Okay, and we can see that this part. So this is using the existing methods like the clustering algorithm. You can see English has like 14% diarization error rate. Spanish had, I mean, for the same audio file I am talking about, Spanish had 12.7% and Chinese had 13.8%. But using our new technique where the data is loosely labeled and we optimized the way we did, we are seeing around 0.8%. Sorry, 8%. Actually, it's not 0.8%. Yeah, 8% diarization error rate. And the best metric, as a best similarity metric, we found was L2 for Spanish, and yeah, you can see against 12.7%, right? And also we could see for English also we could see Kendall's tau. Again, it is I think above 8%, like 9% or 10%. That is for English, and here you can see it is 14%, which is definitely an improvement over the existing clustering methods. But definitely this is not as good as the supervised learning, but keeping the cost and the time saving in mind, this is a better approach, I would say. And we can also see in the Chinese language, it is using the existing clustering methods, it is 13.8. And we have around, yeah, I think again, that is around 10%. So yeah, this is about my paper. I think because I started a bit early, I finished it a bit early as well. So if you have any questions, please feel free to ask in the forum.